Chapter 3 is divided into two PowerPoints, Chapter 3A and Chapter 3B, and this is Chapter 3A. The chapter is Temperature and Humidity Extremes. We're going to be exploring warm days and cold nights, extreme heat, extreme cold, daily and regional temperature variations. We're going to talk about weather extremes and human discomfort. We sure know about that, especially in the summer. Humidity. Dew point extremes. What is the dew point? How does that deal with relative humidity? And how humidity or moisture in the air dictates human comfort or discomfort, which we certainly know a lot about here in Fresno in the summer. Talk about warm days, first of all. Air is a poor conductor of incoming solar radiation. So initially, the heat that comes from the sun only affects the air within a few centimeters above the ground, and that's why the world standard for measuring air temperature requires that thermometers be in an instrument shelter, properly placed, about 1.5 meters above ground level, just about eye level, so that you don't get extremes in temperature. So that's how we get accurate readings, by putting the instrument about 1.5 meters above the ground in a proper instrument shelter. Now, if the winds are calm on an afternoon, you get much larger temperature contrasts between the surface and just a few meters above the surface, as opposed to a windy afternoon, which is represented on this graph by the purple line. The wind tends to mix the layers of the atmosphere more efficiently, so you don't get as big a temperature contrast between the surface and a few meters up. It really depends on the surface. Now, this figure shows temperature profiles for each condition over asphalt. So asphalt's quite different than, say, grass. The exact time of day that the high temperature occurs at any place varies considerably from place to place and from time to time. Now, typically under clear skies, the high temperature occurs around mid to late afternoon when incoming solar energy is decreasing and outgoing long-wave radiation from the Earth's surface is increasing. Where those two lines meet is where the high temperature typically occurs on a clear day in mid-afternoon. Lots of variables can affect this, though. Humidity, clouds, storms, geographic location can affect all of this, and we'll discuss this as we go deeper into this course. Now, as you might imagine, Fresno is one of the hottest places in the United States. The average high temperature in Fresno in July is 98.1 degrees Fahrenheit, and Table 3.1 on page 65 lists the hottest inhabited places in the United States with a population of at least 45,000 people. Palm Springs is the hottest, largest major metro area in the U.S. And there you go. Fresno is on that list. How about that? No surprise there. Now, Figure 3.5 in your textbook shows that the world's highest temperature is 136 degrees Fahrenheit, 58 Celsius at El Azizia, Libya. Now, recently this has been found to be erroneous data. Death Valley, California has the record of 134 degrees Fahrenheit, 57 Celsius. If you click on the hyperlink, you'll be able to explore the recent article just issued just a few months ago having to do with this scientific determination by meteorologists that Death Valley, California holds the record for the world's highest temperature at 134 degrees Fahrenheit. Now, let's cool you off a bit and talk about cold nights. Once the sun sets, there's no longer incoming solar radiation, only outgoing long-wave radiation. Radiational cooling occurs as long-wave energy, infrared energy, is emitted by the Earth's surface. That's the energy that has been gathered by the Earth from the sun during the day. So what happens is that a radiation inversion often sets up, especially on nights where skies are clear and the winds are calm, where the temperature at ground level is much lower than it is just a few meters above the ground. This is very common on clear, calm nights just about any time of the year, but especially accentuated in winter. These radiation inversions are a whole lot more likely on clear, calm nights as opposed to clear, windy nights when you have mixing of the layers. Lowest temperatures are experienced, of course, in winter when we have low sun angle and less daylight. So once the sun sets, the Earth cools off very rapidly, sets the stage for the radiation inversion, especially if there are no clouds and very little wind. If these radiation inversions are persistent, especially if a very cold air mass has invaded a region, then farmers get worried about frost protection, which of course is critical for our local crops, especially here in the winter and early spring. Radiation inversions are especially enhanced when the coldest air sinks to the bottom of a valley. The warmer air above the cold layer right down on the bottom of the gully there, is called a thermal belt. If you go east of Fresno on Highway 180, you can notice that as the elevation increases, there are actually some citrus orchards on those hills. That's because farmers know there's a thermal belt there, and it's typically a little bit warmer than it is right above the basin floor. Now, if you want to talk about extreme cold in the United States, this table, 3.2, shows the average January low temperatures in degrees Fahrenheit for some of the coldest places in the United States. Well, it's no duh that Fairbanks, Alaska takes the cake at minus 19 degrees Fahrenheit. The largest coldest metropolitan area in the U.S. is Minneapolis, with an average low temperature in January of 4.3 degrees above zero Fahrenheit. Now, if you want to talk about record low temperatures globally, you can explore this. It's in your textbook. There are some records that you can examine. We won't belabor that issue here. Let's talk about daily temperature variations. Obviously, there are so many degrees every day between the low temperature and the high temperature. The difference between the minimum temperature and the maximum temperature is called the diurnal temperature range. Now, the largest diurnal temperature ranges occur on high elevation deserts where the air is dry. You typically have cloud-free conditions, and there's very little water vapor in the air. The lack of water vapor in the air allows the temperature to soar during the day and cool off rapidly during the night. When you have clouds and humidity present, that has a large effect on the daily range in temperature. For instance, in the summertime, you would expect a place in like Phoenix to have a much greater diurnal or daily temperature range because of the lack of humidity than, say, Miami, which is very, very humid. You might have a range of 30 degrees Fahrenheit between the low and the high in Phoenix in July, but in Miami, you might only have a daily or diurnal temperature range of 15 degrees Fahrenheit because of the moisture, the humidity in the air. Cities near large bodies of water typically have smaller diurnal temperature ranges, as I just explained. Clouds versus no clouds. This is a biggie. If you have clouds present, that tends to keep incoming solar radiation from reaching the surface, keeping the daytime temperatures cooler than they would be otherwise. And at night, that same cloud cover will bounce back to the surface, long-wave radiation that can't escape into space because of the cloud cover. With no clouds, which is the second figure on the right, that allows days to be warmer generally and nights cooler, which produces larger daily or diurnal temperature ranges. That's pretty self-explanatory. Cities actually generate their own warmth, often much warmer at night compared to the surrounding countryside, due to the fact that long-wave radiation coming off concrete and asphalt at night keeps cities generally a little warmer, and that creates what's called an urban heat island. I've seen this myself. For instance, I've driven, say, from downtown Fresno on a cold winter morning where my car thermometer might say 30 degrees Fahrenheit at daybreak, but say out northeast of Clovis, out toward Quail Lake, it might be 22 or 23 degrees at the same time. So this is a real thing that happens, the urban heat island. The average of the high and low temperature for any particular 24-hour day, which is officially midnight to midnight local time, is called the mean temperature. So if the high is 90 in a particular day and the low is 60, that means the mean is 75 Fahrenheit. Now, there are regional and seasonal temperature variations which involve what we call controls of temperature. This has a lot to do with the angle of the sun above the horizon. That has to do with latitude. And also, it has a lot to do with how much daylight you have. We have less daylight in winter than summer, so that's a control of temperature. A biggie here is land versus water. All right, here's the deal. This is a very important concept. Water has a higher specific heat than land does, dirt, okay? And water is mobile, so it takes a lot longer for the surface of a body of water to heat up to the same temperature as the temperature of the dirt on the surface. Ocean currents are major factors in distributing heat energy through the Earth system. There are warm ocean currents and cold ocean currents. Elevation has a lot to do with it. Obviously, the higher up you go, generally the colder it gets, and that initiates cooling, and increased diurnal and seasonal range in temperature the higher up in elevation you are. Controls of temperature, very, very important concept. Take a look at this chart. It shows the average January temperatures in degrees Fahrenheit around the world. This is at sea level, okay? So we had to sort of reduce that to sea level. Now watch as I make the transition from January to July. Watch how this changes. See how it shifts northward, and you start getting the hottest temperatures, of course, during northern hemispheric summer. Also remember that the northern hemisphere has more land than water, which is crucial. A crucial difference. So those extremes in temperature are much greater in the northern hemisphere seasonally than they are in the southern hemisphere. Once again, ocean currents, going back to that. Ocean currents distribute about a quarter of the Earth system's heat energy around the world. The warm currents are indicated with red arrows. They move from the equator toward the pole. The cold currents, which are indicated in blue, move from the poles toward the equator, so you can see how the heat energy is distributed in the oceans. Note that the big temperature contrast along the west coast of continents in mid-latitudes during summer. Now that means right where you live, because we have a cold current, and that's due to the upwelling of cold water near the coast of, say, western South America and western North America, which we'll explain in more detail in a later chapter. The California coast in summer in July and the coast of Chile in their summer in January are perfect examples of this cold ocean water upwelling, which gives us big seasonal and diurnal temperature variations because of those cold ocean currents. Now here's an interesting series of 3 charts. The annual range of temperature. This is a very important concept, which means is you take the warmest month, the average temperature for the warmest month, or the mean temperature for the warmest month, and you subtract from it the mean or average temperature for the coldest month. And since all 3 places we're seeing on these charts are northern hemisphere locations, the coldest temperatures tend to be in January and the hottest temperatures tend to be in July, except for San Francisco, which is a slightly different case because of that cold ocean current. Notice figure 3.14, that's Winnipeg. They have a much larger annual temperature range due to the high latitude. They're at 50 degrees north latitude or so. Even though Bergen is 10 degrees farther north in latitude, they have a smaller annual temperature range because of the warm ocean current. That's the North Atlantic drift that comes originally from the Gulf of Mexico and the tropical waters of the Atlantic. And then you look at San Francisco, which is altogether different. The annual temperature range is small, and the warmest month appears to be right around September. And that's because finally those cold ocean currents along the coast, the California current from the Gulf of Alaska, start to relent a little bit, allowing finally for some warming in San Francisco. Next PowerPoint is Chapter 3b, and we will continue to explore global temperature extremes in more depth when you look at that PowerPoint.